Hello, Gen Chemers. We're back with more lecture pertaining to Module 4. So let's get started. To continue our conversation, we're going to be looking at nomenclature. So we want to be able to name compounds, whether they're molecular or ionic. And there are rules for naming various types of compounds. So let's start with sort of a general comparison of molecules and ionic compounds. Molecular compounds are usually composed of two or more covalently bonded nonmetals. The basic unit of the molecular compounds are molecules, and those molecules are composed of the constituent atoms. So water is composed of H2O molecules. Dry ice is composed of carbon dioxide, which is CO2 molecules. And propane has a molecule that has 3 atoms of carbon and 8 atoms of hydrogen bonded together. So C3H8 is its molecular formula. Ionic compounds are composed of cations, which result from metals losing an electron, and anions, which result from one or more nonmetals gaining an electron. It's those electrostatic charge between those oppositely charged ions that form the ionic bond. The basic unit here is the formula unit, which is going to be that ratio, that gives me the smallest ratio of my electrically neutral collection of ions. So in an ionic compound, the charges on the positive cations must balance the charges on the negative anions, because ionic compounds are net neutral. So if I have a sodium plus and a Cl minus, I have a 1-to-1 ratio, which gives me that net charge equals to 0. Here's some graphics. This is what a propane molecule looks like. Basically, I have 3 carbons connected to each other, and then I have hydrogens surrounding the carbons, but this would be propane. And then sodium chloride, where I have a sodium plus and a Cl minus combining together. And again, I've got this crystal lattice where I have my sodium ions surrounded by multiple chloride ions in that 1-to-1 ratio, which gives me a net 0 charge. There's also a species of ions called polyatomic ions. Many common ionic compounds contain ions that are themselves composed of a group of covalently bonded atoms that has an overall charge. These are going to be polyatomic ions. There are many charts that you can find. I will post one of my favorite polyatomic ion charts on our course management system. This group of charged species is called my polyatomic ions. For example, NO3 is an aggregate of nonmetals, nitrogen bonded to 3 oxygens, and there's a net negative charge. So this would be a polyatomic anion. CO3 is carbonate. I have carbon bonded to 3 oxygens, and I have a net -2 charge. That would be carbonate. So this is the nitrate ion. This is the carbonate ion. This parentheses indicates I have 2 of these ions, which are ClO3 minus, this is going to be my chlorate ion. So these specific polyatomic anions have separate names. Those names and charges and formulas are things that you need to become very familiar with because we use them routinely in this class. So let's see how we can put ionic compounds formulas together and then how we can name them. So there's a bunch of rules that we have to consider. This is a summary slide, which basically looks at the formulas of ionic compounds. I always have positive and negative ions. So I always have cations and I have anions. Cations are always written first. Those are my positively charged ions, and my negatively charged anions in a formula are written last. Here's an important principle. The sum of the charges of the cations must equal the sum of the charges of the anions. They will combine together in ratios, which gives me a net zero charge on the overall compound. So this formula or formula unit is going to reflect the smallest whole number ratio of ions that gives me this net zero charge. Now, when I look at representative or main group elements, remember I can predict their charge from their group numbers. Representative elements only form one type of charge. Remember my transition metals, which are those elements in the middle, they will form multiple types of charges. So they are not predictable like the representative elements. So I actually have two different sets of rules. Rules for compounds that are formed by representative elements, which form these predictable charges, and then rules for putting compounds together from ions that are derived from transition metals, which I have to have an additional step in order to figure out what charge is actually being used. So let's look at the more simplest case, or the more simple case. Naming ionic compounds. There's two types. This is going to be, the metal forms only one type of ion. This is from my representative or my main group elements. And then these type 2 are from my transition metals, and tin and lead. Those guys are up there as well, tin and lead. I guess I got to the end of that thing. So type 1, representative main elements that can only form one type of ion. Type 2 is a metal that forms more than one type of ion, and that would be typically my transition metals or some representative elements like tin and lead. Remember, the charges on the representative elements, which are the first 2 columns and the last 6, are predictable. Notice, for the most part, when I have these transition metals, I have multiple charges that can arise. For example, manganese can be a +2 and a +4. Cobalt can be a +3 and a +2. But notice I also have these representative elements that also can form multiple changes. So these guys are also considered to be type 2 compounds. There's also a few of my transition metals, like zinc, or like silver and cadmium and scandium, right? These are going to be type 1 metals because they only ever form one charge. There's no multiple charges there, so I don't have to use the same type of naming system as when I have with type 2 compounds. This is a little confusing. What this whole section takes is practice, which you're going to get a lot of as we go through this module. All right, let's name type 1 ionic compounds. Type 1 compounds contains a metal where the charge is invariant. So these metals always form the same charge. The metal ion always has the same charge. So again, representative elements and a few transition metals based on that chart. Okay. Let's look at some common monoatomic anions. So these are derived from nonmetals. The anions actually sort of change their name when I use nomenclature. For example, fluorine, when it forms an F minus, is called the fluoride anion. So I take the base name of the element, I take the suffix, and I remove it and I replace it with an IDE. So chlorine, Cl minus, goes to chloride. Bromine, Br minus, goes to bromide. The charges don't matter. If I make a sulfur 2- charge, it's called sulfide. Oxygen 2- is oxide. So I'm going to use the root. Nitrogen 3- is nitride. So I need to use the periodic table in order to figure out the name of these anions. When they're just elemental anions that are representative nonmetals, I can predict the negative charge that they form, and I can take the base name of the element and then replace the ending with an IDE, and then I have the name of the anion. So let's look at binary compounds. Binary means two. So it contains only two different elements. So I have a metal and a nonmetal, which are based off of elements on the periodic table, okay? To name these things, I just take the name of the cation, which is the name of the metal. And then I use that base name with this IDE ending. That's the rule. So an example, remember with ionic compounds, it's neutral. So the total number of positive charges must equal the total number of negative charges. If I combine sodium and chlorine, sodium will form a +1 because it's group 1A. Chlorine will form a -1 because it's group 7A. I name the ion, which is the metal name, sodium, and then I name the root name of chlorine, which is chlor, plus IDE. It's a 1-to-1 ratio because I have 1 plus and 1 negative that cancel out to form 0. So my formula ratio, right, is NaCl. It's 1 sodium plus and 1 Cl minus. Let's look at if I look at magnesium and oxygen. Magnesium is in group 2A, forms a +2. Oxide, so this is 2A, this is 6A, it forms a -2. Notice +2, -2. I only need one magnesium 2+ ion and one oxide 2- ion in order to combine. That's also a 1-to-1 ratio, because here I have a 2 plus and I have a 2 minus, and that's gonna combine to form 0. I don't worry about the ratio of combination when I name things. I just worry about what's the metal name, magnesium. What's the ion name, or the anion name, oxide. Notice when I have aluminum, which is in group 3A, that'll form a 3 plus charge. And sulfur, which is in group 6A, will form a 2 minus charge. So here I have 3 plus, and here I have 2 minus. I actually need 2 3 pluses, which will give me 6 plus. Then I need 3 2 minuses, which will give me 6 negative to get 0. So the ratio that gives me the lowest whole number ratio of ions that gives me a net neutral formula is Al2S3, right? Notice some people like to use the crisscross method, which is a gimmick. I like you to understand what's happening. I need 2 aluminum plus 3s to balance out 3 sulfur 2 minuses. That's the lowest whole number ratio. Notice these subscripts that give me the ratio of the ions are not reflected in the name. The name is going to be the metal, which is aluminum. The anion from sulfur is called sulfide, aluminum sulfide. I don't need any Roman numerals here. In these simple binary type 1 compounds, I don't need any mono, di, or tri type prefixes. It's simply the name of the metal and then the name of the anion with an IDE. Now the second type, type 2 ionic compounds, where I have a metal that can form more than one kind of cation. This depends on the compound. In this case, because I have more than one cation that can be formed, I have to specify the metal charge for a given compound. The ratio, the proportion of metal cations to nonmetal anions help us determine the charge on the metal. These really don't vary. The anions are always known. It's these transition metals that can vary by losing different numbers of electrons to become cations. So for instance, iron can form a +2 or a +3. Here, my sulfur ion, I know, is 2 minus. I know that because it is a group 6A metal. It's a 1-to-1 ratio. So my iron has to be a 2 plus charge. So I'm using the charge on the sulfur ion in order to figure out what the charge of the iron cation is based on the ratio in the formula. Here, I know that sulfur is always -2, and I have 3 of them, so that gives me a -6 charge overall. Let me make that more clearly negative because it looks kind of positive. A -6 charge. Well, I have 2 irons. So the 2 irons themselves have to give me a +6. So that means that each iron has to be a +3 to give me the +6. So again, I'm using the anion in order to figure out in that particular compound what the charge of the cation is. Let's look at this one. This oxygen is always a 2 minus. I have 2 coppers, so each copper is going to be a 1 plus. See, I need 2 copper +1s to balance out 1 oxygen 2 minus. That's why I have this subscript here. I know that oxygen is a 2 minus. This is a 1-to-1 ratio, so my copper has to be a 2 plus. So now in these formulas, I've determined what the charge of the ion is. So now I have to put that together with how I can name it. Now, some main group metals, like these guys, form more than one type of cation. So I have to make sure that I use the rule that's appropriate for the type of cation that's being formed. So once I have those charges established, I put them together in a name. The full name of those type 2 ionic compounds that contain metals that form more than one kind of cation follow this form. The name of the cation, which is the name of the metal. This is going to be a parentheses with a Roman numeral. And that's how I represent the charge of the cation. And then this is the same, the base name of the anion followed by IDE. Remember, the charge of the metal can be determined by inference based on whatever that non-metal anion is. So, for example, when I want to distinguish between iron 2 plus and iron 3 plus, the name of the cation is going to be iron parentheses Roman numeral 2 close parentheses for iron 2 plus, and iron parentheses Roman numeral 3 close parentheses for iron 3 plus. So those other compounds that we just talked about that were back here, FeS and Fe2S3, if I do FeS, I have iron 2 sulfide, and I have Fe2S3. I call that iron 3 sulfide. Here are some of those metals that form these different charges and what charges are actually formed. This is the column you really have to focus on because this is what we currently use. We use the Roman numeral parentheses charge to designate these different charges. This is an older name where the OUS is the lower charge and the IC is the higher charge in terms of integer value, right? So +2 would be the chromous ion and +3 would be the chromic ion. These actually are not used very often, and it's really good that this isn't used because you'd have to know that chromium forms +2, and that's the lower charge in order to correctly name this ion. You have to know that the higher charge is a chromium 3 plus, which gives us the chromic ion. With our system using the Roman numerals, I don't have to know that. What I have to know is I know that whatever charge it is, the charge is designated specifically with those parentheses with the Roman numeral in front of it. So this causes a lot less confusion. So let's go through this. What if I want to name CrBr3? First of all, chromium. This is a transition metal. So the first thing I think is this is going to be type 2 with a variable charge. Remember, the sum of the charges on the formula has to equal 0. I know that each Br is a -1 because it's group 7A. I have 3 bromines, which gives me -3. I only have 1 chromium. That means my chromium has to be +3. My bromine charge total is a -3, right? This is for bromine. So to balance out that -3, I have to have chromium as a +3 charge. So this is called chromium 3. The name is going to be chromium, parenthesis, Roman numeral 3, close parenthesis, space, bromine. Here's some examples. If I have iron 3 oxide, this tells me I have an iron 3 ion. This tells me I have an O2 minus from the predictable charges representative. If I want to figure out the formula, I have to figure out how they're going to combine. I'll need 2 irons, right, which gives me a +3 and a +3, in order to balance out with 2 oxygens, which gives me a -2, a -2, and a -2, right? I have to be able to go from name to formula and from formula to name. I have to be able to go both ways. If I give you this, you're going to come up with this. If I give you this, you're going to come up with this. You have to go through the individual ions in order to do either one of those directions. Tin 2, if it's given in the name, you know it has a 2+ charge directly. If I use the formula, I have a -1 and a -1 from the chloride, which gives me a -2, so my tin has to be a +2. Here's lead 2 fluoride. I need 2 fluorines to balance out that 1 lead. So if I give you lead 2 fluoride, you're going to recognize I have lead 2+ ion. Fluoride is always F-. To put it together, I get the formula of PbF2. But if I wanted to name this, you're going to use the fact that fluorine is a -1 to determine that lead is a +2. You're going to use the name of the variable lead ion, which is lead parenthesis, Roman numeral 2 close parenthesis, and then followed by the anion. So again, you need to go both ways. To practice, right? Here, this is representative, this is representative. It's going to be sodium chloride. This is transition metal, this is representative. So I have 3 -1s, which gives me a -3. So this is going to be the chromium 3 chloride. That's very similar to one that we did before. Now, what if I had to write the chemical formula? Zinc nitride. Zinc is a transition metal, but it always forms a 2+. So zinc always forms a +2. Nitrogen is a representative metal. It's in group 5. Oops. It is in group 5A. So it forms a 3+. So my nitride is N3-. Knowing these charges, what formula do I get? I can use this sort of crisscross method, or I can think of the fact if I have zinc, I need a +2 and a +2 to give me a +6, which means I need 2 nitrogens to give me a -6. I don't know why I can't speak. So the formula here would be zinc 3, N2. I have 3 zinc 2 pluses. I have 2 N3 minuses. This gives me a +6. This gives me a -6, which is my lowest whole number ratio. So this would be the formula. Copper 1 tells me I'm using a copper +1 ion. Oxide, which is group 6A, gives me an O2 minus. Well, this is easy to see. I need another copper +1. So the formula here is going to be copper 2 oxide. And that's going to be the chemical formula of that particular compound. Now, what about if I have polyatomic ions? I'm going to name ionic compounds that contain a polyatomic ion in the same way, but I'm going to use the name of the polyatomic ion. You need to have a chart. Look up a chart of polyatomic ions and then try to use it all the time you do homework. If you were taking this class face-to-face, you would have to memorize that chart. But since all our tests and quizzes are going to be online, we will not have to do that. But you will need to know these. If you plan on taking Chem 2, you will need to know the names of polyatomic ions, the formulas, and the charges. So for example, in this formula, I have the cation and I have the anion. The anion has 2 nonmetals bonded together. This N2 minus is the polyatomic anion, and it's called nitrite. I know this because I'm getting it off of my chart. At some point, I'm just going to remember that. So this compound, I name the metal sodium, I name the anion's name is nitrite. My polyatomics are always going to have an ITE or an ATE ending for the most part. There are exceptions that you have to worry about. This is an example of a chart that I'm talking about. Here's my nitrite, which was NO2 minus. Notice that ending is ITE. Here's a nitrate. It almost looks identical, except I have one more oxygen. That NO3, still with a -1 charge, is called a nitrate. You're going to see this a lot. Sulfite, which is SO3 2 minus. Sulfate, which is SO4 2 minus. I have the same charge, but one more oxygen. If I put a hydrogen in front of a polyatomic, for example, I go from carbonate, which is CO3 2 minus, I put a hydrogen. A hydrogen basically is a +1. If I put a hydrogen and I connect it to the CO3 2 minus, I'm adding a plus, so my charge goes to -1. The hydrogen goes in the front of that formula, and notice I have the name hydrogen carbonate included. This hydrogen could also be represented by bicarbonate. This also happens anytime I put a hydrogen in front. Phosphate, which is PO4 3 minus, I put in a hydrogen, I add a plus charge, so my charge becomes 2 minus. The name is hydrogen phosphate or biphosphate. Because this is -3, I can add a second hydrogen. Now I add another plus, I go down to -1. that name, this is one of the only times I use these prefixes in ionic nomenclature. The name of the ion in this case is dihydrogen phosphate. Notice if I have, where can I write this? PO3, 3 minus, this would be phosphite. Again, one less oxygen than the phosphate, but I could have hydrogen phosphite and dihydrogen phosphite as well in the same analogous way. Ammonium is my only cation on my polyatomic charts. Cyanide, peroxide, and where is hydroxide? Those are the only IDE endings that happen to be polyatomic. I have multiple atoms and a charge, and the atoms are all nonmetals. So watch out for those ones where I have an IDE ending, but this is not hydrogen, hydride. This is hydrox. That OX means I have oxygen. So this hydroxide ion is going to be one we use a lot. So let's see how you can sort of look at those charts and come up with patterns in order to help you remember those names. Most of the polyatomics are oxyanions. So they're going to contain oxygen, that's the oxy part, and then some other element. When a series of oxyanions contain different numbers of oxygen, they are named according to the number of oxygens on the ion. If there are two ions in the series, the one that has more oxygen ends in ATE. The one that has fewer oxygen ends in ITE. So for example, nitrate, I have 3 oxygens. Nitrite, I only have 2 oxygens. The charge is the same in the series. Notice sulfates is 4 oxygens. Sulfite is 3 oxygens. The charge is the same in the series. If there are more than 2 ions in the series, I have to use a prefix that means less than, that would be hypo, and a prefix that means more than, that would be per. So this is a series where I have chlorine attached to oxygen, and I have 1, 2, 3, or 4 oxygens in these ions. The middle 2 are sort of my standard, right? Bromite, bromate. Notice this is different from Br minus, which is bromide. The ite and the ate imply oxygen, right? These are oxyanions. The hypo here says I have, notice I have an ITE ending. This says I have 1 chlorine less than my chlorite, hypochlorite. Here's my 8, which has 1 oxygen more than my ite. More than 8 is perchlorate. These series can be used for chlorine, for bromine, also for iodine. Notice the charges are all -1 and they don't change regardless of how many oxygens I add. So you can remember this series by writing the halogen O, halogen O2, halogen O3, halogen O4. They're all -1, minus, 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 minus. The 2 in the middle is the regular ite and ate. The one that has the fewest is hypochlorite, 1 less than the ite. The per is the one that has the most oxygen. Per meaning more than the 8, perchlorate. So hypobromite, bromite, bromate, perbromite. I can do the same thing with iodine. Hypoiodite, iodite, iodate, perbrom, or periodate. So this is how I'm going to put them together. If I'm combining Na plus and OH minus, 1-to-1 ratio. I have one positive, one negative charge. My formula is NaOH. I name the metal, which is sodium. I name the anion, which is hydroxide. If I look at this next example, right, magnesium carbonate. Magnesium forms a 2+ because it's in group 2A. Carbonate is my CO3 2-. +2, -2, it's a 1-to-1 ratio. Notice I write just MgCO3. To name it, I'm using magnesium carbonate. Here, if I look at sodium carbonate, sodium is my representative, always forms a +1. Carbonate is a 2-. I need a 2-to-1 ratio in order to get this to be net neutral. So I need 2 sodium ions for every 1 carbonate ion. Notice if I had that formula, I just name the metal sodium, I name the anion carbonate and put them together. Here is one of those type 2s where iron can form either a +2 or a +3. Here, this tells me with the Roman numeral parentheses 2, I have the iron 2+ ion. So now I need a 1-to-2 ratio because this is a negative charge. So I need 2 hydroxide ions. So when I do that, I'm going to draw a parentheses around the ion, and I'm going to put that subscript outside. This tells me I have 2 of those ions. So that when I have more than one polyatomic ion, I put the ion in parentheses, and then the number of ions present in the compound is a subscript that is located outside the parentheses. So basically that tells me I have an iron 2+, and then I have 2 OH minuses. And that's how I get to that formula. So let's practice. Write the names of the following compounds. Well, chromium is a transition metal. That's a variable charge. So I need to figure out what this ion is and what the charge is. We just talked about that. ClO4 -1 is perchlorate. There's 3 of them, so I have a -3 charge when I count up all my anions, which means this must be chromium 3 perchlorate. Here is my only cationic polyatomic ion. This is ammonium, which is a +1. This guy, NO3 -1, that's got the more oxygen, so it's nitrate. So I would call that ammonium nitrate. So those are the answers to those namings. For the chemical formula, I'm going to look at lithium. Lithium has a +1 because it's in group 1A. Bicarbonate is my polyatomic. if you look at the chart, that's HCO3 minus 1. That's going to combine in a 1-to-1 ratio. So my formula would be lithium, and then I just write by the bicarbonate ion. Calcium is going to be calcium 2+, because it's in group 2A. Hypobromides, that's going to be BrO-. So I'm going to need 1 of these and 2 of those. So I'm going to put this together like that. Oops. Like that. Sometimes you might find that the oxygen and the bromine are switched. It depends on what source that you're actually looking for. So you may see that as CaOBr2. At this point, we're going to stop, and then we've got enough to worry about at this point. We will continue with our naming exercises using different classes of compounds when we return. So I will see you guys later, and happy studying.